So we're going to talk about some aspects of chemical kinetics. I'm going to start with some principles that affect reaction rate, and then we'll get into more mathematically oriented principles. And finally, we'll finish with a discussion of mechanism and how that mechanism relates into organic chemistry reactions from the context of sequence of events that correspond to conversions of reactants to products. So really, chemical kinetics is designed to answer that question, how fast will I obtain my products? And so where we really want to begin with this are factors that influence reaction rates. And even though we're not committing to those rates being faster, by default, that's really what we're referring to. So here are some of the important factors that affect reaction rate. Number one, the concentration of reactants. When I increase the concentration of reactants, I will increase the reaction rate. Now, this is pretty easy to see if you subscribe to simple collision theory. So the idea in chemical kinetics is that if I change a factor that will result in more collisions between reactants, I will increase the rate at which reactants are converted to products. So since we're talking about collisions, let's talk about the most famous type of collision that happens in Memphis, and that is running into a knucklehead on 240. You are more likely to run into a maniac the more cars you encounter on 240. So when you're driving on 240, let's say between 7:30 to 8:30 a.m. or between 4 to 6 p.m., you're more likely to be involved in a collision because there's a greater concentration of cars. We can think of cars that are moving yet not involved in an accident as reactants. I'm more likely to have a car involved in an accident when there are more potential cars to collide with. Now, if we convert this back to chemical thought, the more reactants we have, the more collisions we'll have, the more likely we'll have a collision with the right energy and the right orientation to convert that reactant to a product. And we can prove this pretty easily if we look at the reaction of a real nice example is if we were to go to the pharmacy and if we were to get the over-the-counter hydrogen peroxide, which is 3% hydrogen peroxide. Hydrogen peroxide comes in 3%. On eBay, we could order 6%. From a chemical company, 30%, and it comes in a special container. But if you're really lucky, and I have been in my life, you can come across 50%, and that's when the fun really begins. Now, most of us have had hydrogen peroxide, 3% solution that has been poured over a cut. It will sting just a bit. It is an oxidizing agent, and it will bubble. Hydrogen peroxide breaks down to water and oxygen gas. So H2O plus O2 are the decomposition products of H2O2. This is literally what's happening when you pour peroxide onto a cut. Now we need a balanced chemical equation. 2 molecules of peroxide will give me 2 molecules of water and 1 molecule of O2. At this time, I want to show you just how vigorous this reaction can be when, one, we use 30% peroxide, 2, we use a catalyst. Usually iodide ion is a great catalyst. And 3, we trap the oxygen as soap bubbles, so we'll put some liquid detergent. So there's some really nice YouTube videos that illustrate this process. I simply want to show one in particular. So here's a demonstration of the elephant toothpaste reaction. I already the O2 very, very quickly. Let's take a look at that one more time.
Hey, what's going on, guys? So I'm going to go ahead and start this off with a little bit of disappointing news for you. I literally stayed up all night last night trying to measure out half a cup of the 20 volume hair developer.
Go back to the previous video. And I'm going to pause it and try to explain what we're doing at each small step.
Next, we're going to put a couple drops of food coloring inside, and that's optional. You don't have to do that. Now we're going to put in a good-sized squirt of dish soap. Once you do that, you're going to want to swish it around in there and get it nice and mixed up for about 30 seconds. In a clean and separate container, we're going to mix 1 tablespoon of the yeast.
Okay, here we go. So once we get to all the reactants, I'm going to pause this. In this beaker is a solution of either potassium iodide or sodium iodide. It's iodide ion that's relevant. You have a 30% solution of hydrogen peroxide, and some soap bubbles have been added to trap the O2 gas. And also, the reason these are different colors is that food coloring is often added. This is called elephant toothpaste, where this huge graduated cylinder is like the toothpaste and you squeeze it. So we're going to add the iodine. Incorporated into the first container, and red food dye was incorporated into the second container. So when the concentration of a reactant is increased, the reaction rate will also increase. Let's talk about the effects of temperature, and we've talked about the effect of temperature in the context of thermodynamics and equilibrium, where sometimes an increase in temperature will give us more product, like in an exothermic reaction, and sometimes increasing the temperature, actually let me backtrack that. Sometimes if we increase the temperature, we will get more product, as in an endothermic reaction. So if I have A yielding B, and heat is a product, we know that this is an exothermic reaction. On the other hand, if I have A plus heat that yields B, This is an example of an endothermic reaction. If I increase the temperature, I increase the concentration of heat. That is a stress to the system. Le Chatelier's principle says the reaction will respond to offset that stress, which means decrease heat. So in an exothermic reaction, that means I favor the side that doesn't have heat, which means I will make less product. The equilibrium constant will actually decrease when I increase the temperature for an exothermic reaction. However, for an endothermic reaction, again, the reaction will seek to minimize heat. That means I'll make more product. So if I increase the temperature of an endothermic reaction, I increase the value of the equilibrium constant. That is an equilibrium / thermodynamic phenomenon. When we apply temperature changes to kinetics, the effect is the same on kinetics regardless of if the reaction is exothermic or endothermic. So, increasing the temperature always, and I think that's a nice comfort word in chemistry, always increases the rate of reaction. Let's go back to our collision example on Highway 240 again. The more I increase temperature, the more I increase the random kinetic energy of the molecules, the more I increase the speed of those molecules. If I go on 240 and I drive 70 miles an hour, I am less likely to be in a collision than if I go on 240 and drive 170 miles an hour. The idea is that the increase in temperature will promote an increase in the rate constant. It will increase collisions, which will increase the speed at which reactant is converted to product. Ultimately, increasing the temperature increases the rate constant. And I'll have a lot to say about this later once we talk about explicit rate laws and implicit rate laws. Number 3, let's look at surface area. Increased surface area will increase the likelihood of a collision, and since increasing the likelihood of a collision will increase the rate of a reaction, if I increase surface area, I will increase the reaction rate. And we can look at lots and lots of examples with this. We could look at lycopodium powder is a great example. So lycopodium powder is actually an active ingredient in most solid coffee creamers. And you can get this to work with coffee creamer, but you can also buy from eBay pure lycopodium powder. And if I take lycopodium powder and I were to spread some on a desktop and attempt to light it on fire, I would do nothing more than simply singe the powder. But I can increase the surface area if I light a Bunsen burner, put a small amount into a straw, and actually spray the powder over the flame. So I'd like to go to another YouTube video and show you what happens when I increase the surface area.
simulating a grain elevator explosion. This experiment is successful not because the powder is combustible, but due to the fineness of the powder and the tremendous amount of surface area that comes into contact with the flame. Combustion is a chemical reaction, and the more surface area that is exposed to the flame, the faster the reaction. For the reaction, you will need the following: lycopodium powder, a straw, one propane torch. Before we begin, a word about safety. Always, always, always wear safety glasses to protect your eyes. Always wear safety gloves to protect your hands. Okay, let's get started. First, try to light a pile of lycopodium powder. Notice how it will not combust if you try to light it before it has been dispersed.
Alright, last but not least, let's examine the effect.
Then light a torch. Unbend the straw and aim at the flame and blow. The very fine powder is extremely combustible due to its large surface area. Notice how the powder rapidly ignites. Explosions like this sometimes occur on a much larger scale in grain elevators or confined areas, where a great deal of dust is generated and accidentally ignited. You can purchase lycopodium powder at chemkitdepot.com. Thanks for watching, and I'll see you again soon.
The rate of reaction. It will do this by lowering what we call the energy of activation. It accomplishes this by
This is lycopodium powder. And basically this lycopodium powder ignites and flames up like crazy when you light it. But it only lights up when it's dispersed in the air. So it can't really just catch on fire on its own. Let me show you. See that? It just lights up when it's in the air. Do it again. And as you see here, it will not light. And that's how you make a lycopodium fireball. I hope you liked the video. Thanks for watching, guys. New videos every Thursday. Please subscribe if you haven't, and stay incredible. Peace.
equilibrium to be established much more quickly. So there really isn't an effective correlation between kinetics and the Gibbs free energy of a reaction, or the enthalpy of a reaction, or the entropy of a reaction.
Hey guys, welcome back. So you've all seen the Coca-Cola gummy videos on YouTube, right? I guarantee you've never seen one this big. Yeah, right? It's huge. It's bigger than you. Here we are, outside It's Sugar. I'm gonna go get the giant Coca-Cola mold. It is completely 100% gummy. And now, I'm gonna take a samurai sword and slice this baby. So please subscribe to this channel and subscribe to our vlog channel where you'll see more of him and my wife and me having all sorts of fun. I like that. Ready? 1, 2. So thanks so much for watching. Please subscribe and we'll see you next time. Say peace. Peace.
So we'll call this the energy of activation. And this is an uncatalyzed process. Let's say we also have a catalyzed process. And let's say this catalyzed process goes through 2 steps. Notice that the delta G for the red process is exactly the same as the delta G for the blue process. I've not changed it. It's much smaller. In fact, the energy of activation for the slowest part of the catalyzed process will be lower so we'll call this one 1 and this one 2. Will be lower than the energy of activation for the uncatalyzed process. This is how a catalyst works. In this case, we would have transition state number 1. We would have an intermediate, we'll talk about this later, and we have transition state number 2. So that's the difference between a catalyzed pathway and an uncatalyzed pathway. So these are 4 of the really important factors which will affect the